Hello and welcome again to ML6's Hammertime, a series of videos about over-engineering simple projects just to learn something new. In this video we'll deploy our doorbell detector from the last video using Docker and Docker Compose. We'll also add two more parts into the mix, a labeling dashboard and an automated retraining pipeline. Let's start by planning what we want to achieve and drawing this out into an architectural diagram. We can already add to the drawing what we have already made last time, which is our multi-threaded model server. It continuously records, processes and runs the model on audio coming from the microphone. Even though it does all of this pre-processing on board, we'll just keep calling it model server for now. Over time, the model will generate lots of predictions. Some of them will be correct and others will be wrong. We want to capture these predictions and save them somewhere, so we can label them for later retraining. For the labeling, we're going to need some kind of web interface or dashboard, since I want to label this on my phone, tablet or PC. We just need an overview of all the different windows that were detected by the model server and allow us to label them as being good or bad predictions. The labeled data should then be fed into a retraining pipeline. Ideally, we can trigger a training run straight from the dashboard, right after we labeled a bunch of clips. The pipeline will take in the original data that we used to train the first model and then add the newly labeled clips to it to create an updated dataset. The retraining pipeline will at least have to do these high-level tasks. 1. It will have to split up the dataset into new training and test set. 2. Train the new model on our updated training set and run it on the new test set. 3. Load the old model, run it on the same new test set, and then 4. Compare the two and somehow let the model server know if the new model is any good. When looking at the architecture overview, we clearly see 3 logic blocks. I'll call those our microservices. We also have 3 data buckets, which in this system are just implemented as folders that are accessible by all 3 microservices. Now that the high-level architecture is kind of done, let's get to creating it. First of all, why use Docker and Docker Compose in the first place? When looking at options on how to deploy your own code, we start with what is called bare metal. It's just a script and you run it. But you'd need specific system packages installed, and different microservices might need different package versions, and when moving the code from one machine to another, you have to manually repeat all of these install steps again. You'd need to set up something that restarts the services when the machine reboots, and pipe all the output to log files you'd need to go through with a text editor. Frankly, it's not ideal. So to address these annoyances, a lot of smart people came up with the concept of the Docker container. It neatly wraps each microservice together with its own little environment, with its own little packages and versions and whatnot. It also makes it easier to run the same thing on another machine. Just install Docker on there. It also makes auto-restarting and logging fully automated. Docker Compose then is just a light wrapper around Docker that makes life easier when dealing with multiple Docker containers that have to talk to each other as well, such as in a microservice architecture. Then there's options like Docker Swarm and Kubernetes that only really come into play when you need multiple machines to work together. We're just deploying a single Raspberry Pi, so Docker Compose will do just fine here. If you have 3 microservices called Dashboard, Model Server and Retraining API, starting them is as easy as running Docker Compose up, and you can control each service easily by its name. To make sure microservices can reach their required data folders, we use bind mounts, which just makes a system folder available from within the container. So if the model server detects the bell and saves the audio clip to the unlabeled data folder, we just make sure that the dashboard has the same folder mounted so it can show the same clips on its web page. Now for our first microservice, the dashboard. For this, we'll use Plotly Dash, a very popular and upcoming dashboard framework that works entirely in Python. The premise is very simple. You have only 2 aspects. 1 is the page layout. Dash has Python functions that look exactly like HTML tags, and you can use Python to build your web page structure, and Dash Bootstrap components to style it using Bootstrap. 2 is the callbacks, and these are best explained using an example. Let's take a text input field. It's defined in the layout. we can attach a callback function to it by setting the callback input to be the content or the children of the input field. If anything changes to the content of the field, the callback function gets triggered with the changed value as its function parameter. Now we can output whatever the function returns back to the web page by defining an output to the callback. Finally, you can also add states to the callback, which the function will get as parameters but which won't actually trigger the function itself. Now we just create a card-style layout we can use to label a bell clip, and create one of these for every unlabeled clip in our unlabeled shared folder. Then we add a button down below to save our labels. The button will trigger a callback function that takes the state of all the cards and moves the labeled audio clips into the correct labeled folder. And that's pretty much it. We can now label newly incoming audio clips and move them into the correct folder for retraining. The second microservice we're going to talk about is the retraining pipeline. We begin by taking the code that we used in part 1 as part of our notebook and clean it up a bit, transforming it into nice object-oriented Python code. In this case, I made a Python class called pipeline that strings together a bunch of different task objects. This modular approach makes it very easy to swap out components that have the same inputs and outputs. If we want to be able to trigger this training pipeline straight from the dashboard, the cleanest way to make this work in a microservice architecture is to use an API. The dashboard sends an HTTP request to the retraining API, which then starts the pipeline and can keep the dashboard up to date on what it's currently working on. For this, I use the FastAPI Python framework. So far, I haven't had a chance to try it out yet, and I wanted to see how it worked. It's been really nice to work with it so far, and it even automatically generates a Swagger documentation page based on the code and Python type hints to guess the variable types. Really cool, actually. However, think about it. If we send a request to the retraining API and the pipeline starts running, won't the dashboard have to wait for the pipeline to be done before it can get any answer? If the pipeline takes too long, we might actually get timeouts, and we also don't really have a good way to communicate the progress of the pipeline back to the dashboard. That's where you should always consider an asynchronous job queue, like Celery or Redis queue. I haven't used Redis queue before, but it promises to be very simple and straightforward, so let's try it out. What happens now is that the dashboard sends a request to the retraining API to start the pipeline. But this time, the API puts that request in a job queue and assigns a job ID to it. The API immediately returns this job ID to the dashboard, and then there is no open connection waiting for the pipeline to complete. Redis queue will then start executing the pipeline in the background, and we can add simple lines like this to update the progress on the job. Now that the dashboard has the job ID, it can send new API calls to the retraining API. But this time on another route, it sends along the job ID and it gets the current pipeline's progress back in return. In this way, we can easily keep track of the progress on the front end, but the retraining won't stop when the dashboard connection fails, because there's no open connection between the two. It's just running in the background. Perfect. Now there's only the model server left to cover. Now that we have a new model trained and it's confirmed to be better than the currently running one, the only thing left to do now is to switch out the models. It might be tempting to restart the model server and point it to the location of the new model. However, ideally we don't want to restart anything and can just do a hot reload. The models are all saved in a single folder. To distinguish between the models, their names are simply the timestamps of their training run. The retraining pipeline will always create a shortcut to the best model, also called a symlink in Linux, and we use a symlink called latest that points to the model that's currently considered to be the best. When the model server is first started, it will only look for the model called latest, and because it's a symlink, it will end up loading the best latest model. But it will also take a checksum of that file. And a file's checksum is a hash consisting of numbers and letters. Two checksums will only ever be the same when their respective files are exactly, bit by bit, identical. Now that we have the model hash in our model server, we can every so often recalculate the hash of the latest file. And if it's not the same, it means a new model has been trained and tagged as being better. Now we can just load this new model while the queues just buffer the incoming windows to be processed. Once the model is loaded, we can just continue processing from those queues. And that's it really. We now have a 3-service Docker Compose stack that will auto-launch when the Raspberry Pi boots, shows us true and false positives, which we can then relabel through a dashboard and use those to retrain the model, which will then be hot swapped right into place in the model server. Finally, the code for this project is freely available on GitHub. Extend and modify it to your heart's content. I personally modified the model server to not only send me a notification on the detection of a bell sound, but also send a request to an ESP32 that's connected to my desk's LED strips. It sure is over-engineered, but honestly, I didn't miss a bell since. Thanks for watching and see you next time.